interchangeably. They are not interchangeable, they're very different things. And if you ever see it being said incorrectly, correct the person, because that's what I want changed in this world. If there's one thing I have. Okay, so power is the rate of doing work, so it's how much kind of effort you put into something. Energy is the amount of work that you do. So say two folk are building a house. One built it in a month, the other one takes a year to do it. The one that's taken a year is not as powerful, but at the end of it, they've both got a house. So the energy is the same, the power, the rate at which they've built the thing is different. So in order to calculate energy, what you have to do is look at the power over time. Now obviously with these things, the power can vary, people turn on and off lights. So over time, the energy consumed by that load depends upon when it's used. Certain things like motors, the power will depend upon how much load you actually put on it. So power can vary with time. Energy consumed will only ever go up. I say consumed, energy is obviously neither made or destroyed, it's just converted. So what we're talking about is the energy consumed, the energy converted from one thing to another to your useful load. So you've got all these different loads. Can you tell me how much energy that those loads would consume if you were to use one of those for 5 hours? Energy is written in watt hours, so it's just the multiplication of power, whatever it was, 8 watts, times 5 hours. And that gives you whatever watt hours. So what I want to do is just get in order.
You just run through the calculation that you've done there.
Consume the least energy over 5 hours.
In what?
Which one would consume
Energies in watt hours?
Power
so just simply multiply power by 9.3 by 5.
So divide joules and divide it by the amount of time in seconds.
What's your energy?
Oh no, that's not right.
No, just to get watt hours, just simply multiply by 5.
So an hour, is it?
That's watt hours, I think, yeah.
Okay, you're going into joules. Right, okay. There are lots of ways of writing energy. When we're doing electricity, we nearly always talk about watt hours and kilowatt hours. So all you need to do is you know your power in watts and you multiply it by the time in hours. That gives you watt hours. So you just multiply the power you've got by 5. You can convert it into joules, which is also energy. Watt hours and joules are interchangeable.
If it was 1 watt for an
as long
hour,
as you convert them correctly.
1 watt, 1 hour.
So yeah, electricity we talk about watt hours and
joules.
And you pay for your electricity in units of 1 kilowatt hour. In the UK, 1 kilowatt hour costs about 15 pence. Okay, so what's the energy consumed in 5 hours for your load here?
We reckon it's 3.125 watt hours.
Good, okay, what's yours? 12.5 watt hours. What's yours here?
46.5.
46.5 watt hours and
171.5.
171.5. So in kind of, I've actually gone through them in terms of how much energy they consume, and they're pretty much all doing a very similar thing. Like none of them are particularly much brighter than any of the others. So the LED light bulb, this was an LED light bulb. This consumes 3.1 watt hours. Yours was a halogen light bulb, very similar amount of useful light. Yours consumed 170 watt hours, something like that. So this is ridiculously more efficient than that. So, but obviously that costs more and they're harder to find. And then fluorescence, they were kind of in the middle. So fluorescence took, well, yours was 12.5, it was quite dim fluorescent light, yours was 46. So you can see the whole spectrum of pretty much, you know, the user is seeing pretty much the same output, like they've got something lit. But this, if you were to build a solar power system using this, your solar panel could be much, much smaller, a factor of 10 smaller, more than that, to do this, virtually the same output. The reason halogen is not very efficient here, you can feel that it gets very hot when it's doing it. A lot of it releases heat.
Why don't you have an LED light bulb in the house?
Few different reasons. LEDs at the moment, they are quite good for directed, very focused light. The problem is that the actual tiny little area that lights up is not very big, and if you try and expand that to a bigger area, it gets very hot, and you can't get the heat away.
So you just have it, loads of little LEDs.
That's exactly what that one is. The main issues in the last couple of years, maybe 2 years ago, just the cost of white LEDs was very high, the cost of manufacture. They're only recently kind of come out, and now the prices are dropping. That was probably about £5 when I bought it last year. Those are about 20p. In time, I mean, these are probably now about £2 rather than, so that's what's happening. Yeah, exactly. I mean, if anyone is changing light bulbs, then I would suggest, I mean, people don't like change, so when we go from incandescent to fluorescent lights, people go, oh, I don't like that light. And it's true, there are times when, you know, the light doesn't look quite right, and LEDs is a very bright, intense light. And it's only now that they're really working on doing a nice warm colour that people expect from a light bulb. So there's social reasons, there's technical reasons, there's mass manufacture reasons why LEDs are not yet. I think LEDs will have a great future. They're pretty cheap to make, very robust.
What about energy-saving light bulbs compared to LEDs?
Energy-saving light bulbs are pretty much fluorescence. So compared to halogen is similar to an incandescent type light bulb, so it's a kind of thermal technology. You're heating up something and it glows hot and also light. Fluorescents are kind of in between. So now most people should be having compact fluorescents. No incandescents are for sale anymore, I think, for standard light bulbs. And then LEDs are probably moving towards the future. But fluorescents are very good for lighting a big space. At the moment, LEDs are less good. Anyway, a bit of a sideline. So hopefully I've explained a little bit about voltage, current, resistance, power, energy. And those are the kind of calculations you're going to have to make if you're designing an electrical system. And those are kind of, you know, it's pretty simple stuff. You don't have to do amazing amounts of maths to do it. I haven't covered power and energy in AC electrical systems because it starts to get a bit more complicated, and I don't think it's really the scope of this. If you want to learn more, find a good book or ask someone a bit more, or ask me later. I don't really want to go into it, I'll just confuse people. Bit on electrical safety, probably should have done this before we started all the electrical things. Electricity is dangerous, it kills people. It also, one of the major problems we have is that it starts fires. And in the UK, about 10 people a year are killed by electric shock. About 3,500 house fires are started by incorrect wiring. So people are really more concerned about fires being started. All electricity is dangerous. Batteries are very notorious for starting fires. They can supply very high currents. They can melt if you put a wire across that battery, it will melt maybe the cable, but it will certainly get very hot and it will burn. Generally, at low voltages, underneath about 100 volts DC, there's not much risk of electric shock. So with the stuff we're doing now, you can touch the terminals and you won't get electric shock, but don't do the same with high voltages. So always respect it and always test it, especially if you don't know if it's live or not. Lead acid batteries we're using here, another bit of safety is they are, as the name implies, they are lumps of lead in acid. And these are sealed ones, but there is the potential, if you short circuit it, it could rupture and throw out hot acid gel, which I don't really want happening. It's unlikely, but if you're using any batteries in the future, just know about it. It's filled full of sulfuric acid. It'll melt away your clothes and give you burns. It's a bit annoying. Okay, right. Do you have a chance I can get a drink of water from somewhere? Yeah. Is that okay? Thanks. Sorry? Charging. Yes, that's true. So also when they're charged, they give off hydrogen. Not these particular ones because these are sealed, but open vented ones give off hydrogen gas, and so that's a flammable gas. And if you don't vent it away correctly, then there is the potential for a build-up of hydrogen gas and an explosion, especially if you have a spark. So that can happen. I'll come on to how you protect a battery in a bit and how we stop all these things. So I'm going to do probably bit more of a talk now. There's not as much practical for a bit. I don't